So it's a pleasure for me to introduce, instead of Rafał, who is unfortunately ill, Mateusz Mazelanik, who will present the recent results from the group or the lab of Michał Parniak, if I may say. They're located just next door. And let's start because we don't have much time. Mateusz, please.
Okay, thank you for the introduction. So the first part of this talk will be concentrated on sensing of microwave radiation with hot or warm Rydberg atoms, or atoms contained in a glass cell like this. And this is actually an illustration of a sensor that we developed in the lab. And this sensor is actually based on converting the microwave field to the optical field. And I will tell you more about that later. But first start with the brief introduction why Rydberg atoms are a nice medium to detect the microwave radiation. So Rydberg atoms are highly excited atoms. So we excite the electron to very high energy state. So the principal quantum number can reach even 100. And because of that, they have very long coherence times. The electron can stay in this state for very long time. And also because the electron is so highly excited, the atoms become very large. They can have like micron size, so we can actually see them with microscope, let's say. And also because the atoms are so large, they will have like, they can have very large dipole moments, so we can have interaction between separated atoms on a long distance. And which is most important for us, the transitions between different Rydberg states span very broad range of frequency, and especially in the microwave range. So we can have transition from radio frequency, which is like hundreds or tens of megahertz, to even a terahertz radiation, by just choosing different Rydberg state between which we will have the transition. And so, and because the atoms have very large dipole moments, the transition can be very strong. So the atoms will be very sensitive to the microwave field. So this is a very nice medium to build actually a sensor of the microwave radiation. And as I said, the sensor that we first developed in our lab is based on microwave to optical conversion. And actually the main motivation behind this kind of devices is to build a link between a quantum computer and optical networks. So the superconducting quantum computers operate at gigahertz frequencies. The qubits are interacting with microwave photons, and the optical networks, of course, work with optical photons, which is which means that the photons have a frequency of hundreds of terahertz. So we need a link to we need an interface to link those two domains, and so for this we need a microwave to optical converter. So people are building, for example, devices like this, which is like mechanical resonator that has mechanical resonance in the gigahertz range, and is also coupled with the optical photons. So this is like a resonator for mechanical resonator, but also like an optical cavity. So it can in a device like that, we can have interaction actually between the microwave and optical photons. But to be honest, this motivation is more like from a fantasy category, because we have enough problems with the quantum computers itself. So it's maybe not the best idea to actually put the interface of the quantum computers right now. We need much more development with the quantum computers. But there is another very more, let's say, yeah, not more advanced, but more realistic application of the microwave to optical converters, which is microwave sensing. So because if we can convert microwave photons to optical photons, then we can use all of the detection methods that have been developed over the years for the optical setup. So we can, for example, have a photon counting, which is very difficult for microwave photons, and to use it to detect microwave photons by just using our converter. So for example, we can say that we can have a photon counting measurement of the microwave background radiation of the universe. So for example, we can design an experiment which can measure a correlation between the different parts of the universe and see if there is something quantum in there, and things like that. We can also use the sensors to build like radio links, but with the optical readout. So we can have like a communication at the radio or gigahertz frequencies with the optical detection. And this all started with this very simple approach to the microwave sensing with Rydberg atoms, which is based on this ladder type transition. So we choose just 3 levels of the from the atomic energy level structure, and this is for example for rubidium-87 atoms, and so we have two lasers, and first laser couples the atom to the one excited state, which we call intermediate state, and then we have this blue laser that couples this state to the Rydberg state. So if we do that in the glass cell containing the atoms actually at room temperature, we will see a very large absorption line due to the Doppler broadening of the atomic medium. But at the center, we will see this very narrow peak, which corresponds to the effect which is called electromagnetically induced transparency, so which is actually induced by this laser. So by introducing this laser, we can see that the atoms at when this laser comes into this two-photon resonance, so that there is like a zero detuning between this state and this state through those two lasers, we will see this transparency window, and we can use that to build our sensor, because if we couple our Rydberg state to another Rydberg state with the microwave field, we will see a splitting of this line, and this is due to the Outler-Towns effect, which is actually the same as Rabi oscillation between the two states, but seen in a let's say steady state measurement. So, and which is very important here, that this splitting of those two lines is actually proportional to the electric field of this microwave radiation, and also we can actually calculate the splitting. So the splitting is actually the Rabi frequency of this transition, and it is linked with the dipole moment at this transition and the amplitude of the electric field. So which means that we can link the splitting directly to the electric field by just calculating the dipole moment, which can be done very precisely. So we can have self-calibrated measurement. We don't need any additional calibration setup for calibrating the reference field that we actually are measuring. So this way we can build a sensor that has this self-calibrating feature, which means that it will work the same in a different parts of the world without any additional calibration needed. So, and actually, people are started building a miniaturized setup like this, so we can bring your sensor to for example, some to the field and actually measure the microwave radiation in your, I don't know, electronic circuit or your chamber which you use to calibrate your antennas. So that there are some, actually this is a new topic. The companies that are building those setups are emerging, but all of the currently built sensors, which you can actually buy, are based on this very simple idea. But there are more advanced schemes. For example, the scheme that I started talking to you about, which is a microwave to optical conversion. So this is actually the illustration of the setup that we were using. So we are choosing 5 states to do that, and actually using a free laser. So we the first excitation path is as usual with the red laser and the blue laser. So we excite the atoms to this Rydberg state, and then comes the microwave, which excites the atoms from this state to the second Rydberg state. Then we use our third laser, which actually de-excites the atom to this intermediate state. And then, because this whole process is coherent, at the end we have coherence between this state and this state. And if we do it correctly, which means that we preserve that we satisfy the phase matching condition, so the emission actually can happen, we'll see emission at this transition. So at the end, we are absorbing microwave photons and emitting optical photons, which we can detect. So this is more detailed view of the setup. And for the detection, as I said, we can use, for example, a single photon counting, which can be very efficient with very little added noise. So we can truly say that we are virtually counting the microwave photons. Or we can use some frequency resolve detection, which can be actually also phase sensitive. So for example, we can use heterodyne detection. And so
you are doing them at the same time, or no? It's just a concept what you could do.
Yes, this is just a concept that what you can do. We can, yeah. So that
you don't have a switch.
Well, the switch is like we just can unplug the fiber and connect it to the different detector. So, but it could be a switch if you like it. You could also put a beam splitter here and do everything at the same time. So this is the main result from this experiment, and as you can see, we can detect microwave photons across 7 orders of magnitude in the intensity, and down to the actually thermal radiation in the laboratory. So we actually put a microwave field through the antenna to the cell, and we vary the power of the microwave input. And by varying the microwave field input, we can plot this line on which on the y-axis is the flux of the photons that we actually observe coming from the converter. And if we lower the field coming to the antenna to actually this level, we start seeing some radiation that is not coming from the antenna, but we attribute it to the background microwave radiation coming from the lab, because the lab is at room temperature and the mode population at the 14 gigahertz, which we are using here, is like 1,000 photons per mode. So even if we don't put any signal to the antenna, we still will see some photons coming from the thermal radiation, and this is actually what we see. And we also show that the intrinsic noise level of our device is equivalent to a temperature of 4 kelvins. So we can actually, in principle, detect radiation down to the 4 kelvins, like a thermal radiation. And we can also measure bandwidth of the converter, which can be also tuned by tuning the lasers. And so as I said, we observed this additional radiation, which we attributed to the thermal radiation, and we wanted to be sure that it's actually a thermal radiation. So we actually done a calculation, which is on the one side is based on the self-calibration feature, so we can actually calibrate the electric field that we are putting to the cell using this splitting method. And on the other side, we have our conversion scheme in which we detect photons, and the photon flux will be proportional to the microwave flux, and actually to compare those two methods or actually link them, we have to also include the fact that our sensor is more sensitive in one particular direction. This is due to two effects. One is the phase matching, which I told about before, and the second fact is that it's also very sensitive to one particular polarization, which is chosen by choosing polarization of the optical fields, which effectively selects only one optical transition, which is sensitive only to one polarization. Yes. So we have those two factors. The one comes from the projecting the incoming waves onto the chosen polarization, which is a circular polarization. And the second factor comes from the phase matching, and we can actually compute the antenna pattern of our sensor. And as you can see, it is mostly sensitive along this direction. And if we send the microwave from the back, it will be sensitive slightly, but this is a factor of 30 dB. But the polarization is orthogonal actually to the polarization that should come to the front. So by doing this calculation, we can actually compute the expected level of the thermal radiation, and we arrive at this level, and this is our measured level. So we have very nice agreement. So we can be sure that the photons that we are observed are coming from the thermal radiation, and this is not some strange added noise. And because we can actually count the microwave photons, we can do.
And the one you will apply on that plot would be where? The one you actually apply with the antenna? What polarization you?
Oh yeah, so we apply the polarization that is yeah.
So it's the 0 degrees.
Yeah, and the radiation from the antenna comes from this direction. So we assume that the radiation from the antenna is a plane wave. So so we can count the microwave photons. So we can do some photon statistic test on the radiation that we observe. And this is one example of such an experiment. So we actually calculate the G2 function for the microwave photons. And as you can see, it almost reaches 2, which is good because G2 function for that thermal radiation should be 2. So this is another proof that we are detecting thermal radiation. And we can also play a little with the statistic by introducing the coherent microwave field. So this is the field coming from the antenna, which is mixing with with the thermal radiation from the lab. And as you can see, we can have this nice transition from the thermal radiation, so thermal statistic, to the coherent statistics, which is G2 equal to 1. And we can also introduce a slightly detuned coherent state and observe this oscillation in the statistical function, which is nicely explained by the theoretical model. And more recently, we also done this experiment at a much higher frequency, so which you can actually call at terahertz regime. So in this regime, the antenna pattern is much narrower, so we can actually have like a terahertz or a microwave beam coming to the setup, which is much easier to control. And we actually done this very fun experiment, and in which we are putting something very cold to the microwave beam. And as you can observe, if we put like a very cool black body to the beam, we can observe the drop in the radiation that we observe, the drop in the photon flux coming from the converter, which means that the level of the thermal radiation has been lowered. So this is another different demonstration that we are detecting the thermal radiation. So by just putting something cold in front of the converter. And as I said, we at the 130 gigahertz, we can work with like a microwave beam, and for it we can also build or design optical like elements, for example lenses to control the shape of the beam, and also wave plates to control the polarization of the beam. So this is actually, those are actually wave plates that we made in the lab. So this is like a terahertz photonics, in which we designed the structure to have birefringence. So we have different index of refraction for different polarizations, and that way we can build, for example, a wave plate that will look like this. So this is like a comp structure which has been calculated to introduce pi phase shift for the 130 gigahertz field for one of the polarization. So it's at the end it's like a just wave plate, half a wave plate to be precise. And actually, we can actually test the wave plate and see that indeed the wave plates rotate the polarization and with nice contrast. So this is another demonstration which is using the most basic approach with the splitting. So in this experiment, we can actually take some chip that is used to actually detect the presence of the driver in the car, or actually because the wavelength is so small, the wavelength at 130 gigahertz, which is this chip is operating at, is like around 2 millimeters, which means that you can actually detect if the driver is breathing. And so those kind of chips are put in the cars to detect if the driver is fine, and we can actually show that we can build a setup that can be used to calibrate those sensors and also compare one sensor to another in a very simple way, but just using the simplest self-calibrated method. And so the more advanced method that actually derives from the simplest method, which allows phase sensitive detection, because the method with the splitting is only sensitive to the intensity of the field. and we cannot detect the phase of this of the microwave field using this method. So, for example, we cannot build a radio receiver using that, but we can improve that method by introducing a microwave local oscillator to the setup. So we have two microwave fields at this transition. One of them is the local oscillator, which is usually strong. And the second field is the field that we want to detect, which we call a signal, and is weak. And because the two fields are coupled to the same transition and they are slightly offset in the frequency, we'll observe a beating between those two fields. And the atom will feel the beating, will be transferred actually to the splitting. So the splitting will be modulated. And the modulation will be proportional, the frequency of the modulation will be proportional to the frequency difference of those fields, and the phase will be also proportional to the phase difference between those fields. So that way we can build a phase-sensitive detector, which is also actually more sensitive than this very naive approach. But the main problem with this scheme is that we have to introduce this strong local oscillator, which means that we have to incorporate additional antenna in our setup. And so we can, for example, we cannot build like a detection system that is not disturbing the signal that we want to detect. But that we can use this sensor to, for example, build an atomic radio, which can operate at different frequencies, because we can tune we can address different Rydberg atoms, which will have different transition frequencies between different Rydberg states. So as I said, there is a problem with this super heterodyne sensor that we have to introduce this local oscillator, but we can fix that. So we actually develop a method that is all optical and is also phase sensitive, and is based on the same loop scheme that we are using for the conversion. So in this scheme, we introduce this additional laser at this frequency at which we are observing the radiation coming from the converter. So the easiest understanding of this approach is that we bring the atoms to this Rydberg state using this path and also this path, and the phase between those two states is set by the phase of those laser fields, and then we introduce the microwave field, and again we will observe a beating between this microwave field and the coherence, which is like a microscopic polarization of the atomic medium, which we introduce by using the atomic fields. So at the end, we'll observe modulation of the probe laser. So this is what we done in the experiment, and we can detect this probe field using just a photodiode, and we observe this modulation. But there is one problem here. Namely, the phase of, as I said, the phase of this coherence is set by the phase of the laser taking part in this interaction, which means if the lasers are noisy, which they have like a phase fluctuations, the fluctuation will be transferred to the signal, and this can spoil the signal by very large amount. And as you can see, in the experiment, we actually observe this very broad peak. But so the question is if we can fix that without using very stable lasers, and the answer is yes. We can actually measure the phase fluctuation in an additional process. So we can take a nonlinear crystal in which we can do a similar mixing process, but without the microwave. So we actually generate this 1200 laser in the nonlinear crystal from the blue laser and the infrared laser at 776 nanometer, and we mix the generated 1200 laser with the laser that we are using in the atomic setup, and we observe a beating between the generated field and the field coming from the laser. And because this wave mixing process is coherent, the phase fluctuations of the lasers will be transferred to the phase fluctuation of the emitted light. So if we mix the generated light with the light that we are using in the experiment, we can actually measure the phase fluctuation of all the lasers taking part in this interaction, and we can, at the end, cancel it out. So this is the main result. So we start with this broad signal. We also measure the phase fluctuation of the laser, and those signals are in megahertz range, so it can be easily they can be easily processed using lab electronics. So we can actually in real time how to say this, compensate the phase fluctuation of the signal using this measured reference. And at the end, we can also plot this dynamic plot, in which you can see that we can operate at over 4 orders of magnitude, and we can also compare our method to the super heterodyne approach with the microwave local oscillator. As you can see, our method performs only slightly worse than the super heterodyne approach, but it's all optical. So the factor here is like 3 dB. So now I would like to move to a similar topic, but using a different medium. So worm atoms are nice because the setup can be very simple. You can just take a cell containing the atoms, and you can build your sensor around that. But they have many problems due to the fact that the atoms are constantly moving, and they are moving fast. So we have Doppler broadening, they are colliding with each other. They are leaving the interaction medium, the interaction region, which is the beam that is interfacing the atoms. And so actually to have like a much cleaner situation on the paper to actually predict what is really happening, and also to have like much better control in the experiment. So to be sure that we can prepare atoms in this particular state and then bring them to the other state that we calculated is the best for our experiment. We use a cold atomic setup. So we have cold atoms trapped in the magnetophysical trap. And then we can prepare the atoms in a given state, but just in means of optical pumping. And because the atoms are cooled, then we don't have the Doppler broadening. The atom stays in place, and we avoid different effects that we observe in the worm atomic setup, and which are actually hard to predict and hard to deal in the theory. So the main concept that is important here is called a spin wave. So let's say that we've prepared all of the atoms in the chosen ground state, and then as usual, we illuminate the atoms with this infrared laser and also the blue laser that brings the atom to the Rydberg state. So if we choose very weak this probe laser, this infrared laser, we will excite only small amount of the atoms to the Rydberg state, but we don't know which atoms are being excited. So we have 10 to the power of 8 atoms in the cloud, and only few of them are getting excited to the Rydberg state. So we end up with this state in which we have this is the simplest case in which we excited only one Rydberg atom. But we don't know which atom from the cloud was excited. So we have like the superposition of different contribution, and each contribution is this one particular atom has been excited to the Rydberg state, and those phase terms that are in front of the different contributions are actually the phase difference between the laser fields that are inducing the transition. And this is just due to the fact that the atoms lying at different places in the cloud are interacting with the laser field with different phase because they are in the different position. So if we excite one atom to the Rydberg state, we have this superposition state, and actually the phase factor encode the momentum transfer that has been done during the excitation process. So we absorb 2 photons, and the momentum of the photons is transferred to the atoms. And actually, to bring the atoms back to the ground state, and with coherent emission of a light on this transition, we have to again satisfy the phase matching condition, which can be thought as satisfying the momentum conservation law. So only atoms with a particular spin wave vector, which is momentum, are coupled to the light during the inverse process. And the inverse process is induced by only illuminating the atoms by the blue laser. And this will become very important later. And so one of the basic experiments that we can do in a cold atomic setup like that, so we can, for example, prepare a collective qubit. So we have, for example, one Rydberg atom is excited, but we don't know which of the atoms was excited at the Rydberg state. So we have like collective excitation with only one Rydberg state, and we can treat this state like a qubit. And to do that, we have to introduce another Rydberg state, and again we can have microwave transition between the 2 Rydberg states, so we can control the qubit. So we can bring the qubit to this state, and we can call this state 1 and the lower Rydberg state 0, and we can have, for example, a Rabi oscillation between the 2 states. We can prepare the states in superposition and so on. But the main problem is in those experiments is the lifetime of this collective excitation due to the atomic motion. So the atoms are very, very cold, but they are still moving, and because we have those phase terms in front of the contributions, if the atoms are moving, we will lose the coherence because the phase term will be scrambled, will be mixed, and at the end, our spin wave will be just like a blur spin wave. So we have different, we have contribution of different spin wave modes at the end. And this can be nicely illustrated on a plot which is on this map, which is displaying actually the coherence along the cloud for a different velocities of the atoms. So we start with this linear phase of the atomic coherence, and then if we wait some time because the atoms are moving, we will have this shearing effect. But at the end, during the readout process, we are interested only in the average along the velocities. Okay. So if we wait much longer, then we see that the average is getting lower and lower, and at the end we are left with nothing. And this can actually happen very quickly, and it depends on the on the spin wave vector, so the frequency of those fringes here. So the solution to actually stop this decoherence would be to make this spin wave, the phase of this spin wave constant. So we don't have those fringes, so we always average to nice large signal. So actually to do that, we developed this method, so which is based on modulating the phase of the spin wave using 2 additional beams. So we after the preparation process, so bringing the atoms to the Rydberg state, we illuminate the atoms with 2 additional laser beams that are detuned from these intermediate transitions, and they actually induce a phase shift between the ground state level and the Rydberg level. So during this evolution, we accumulate a phase, and by actually shaping the pattern of which the beams are producing, we can choose the pattern so it actually flattens the spin wave. But so using this method, it in principle could be very efficient if we were able to imprint like a ramp profile. But because the spin wave, which is generated using the infrared laser and the blue laser, has very fast has very large spatial phase frequency of the spin wave, it is very hard to actually design that kind of pattern in the experiment. So instead of a ramp-like profile, we are using a sine wave, which is just interfering 2 beams. But this has a drawback that we are also observing additional diffraction orders of the spin waves. So the first order is hitting the 0 wave vector, which is nice. So actually, it was the second order because it was very hard to make the spatial frequency of this pattern so fast that we had to rely on the second diffraction order to do that. So we are diffracting the spin waves to the second diffraction order, which is actually tuned to hit the 0 spin wave vector, which, as you can see, is insensitive to this decoherence induced by the thermal motion, which is nice. We can show that we have vast improvement over the superfast thermal decay in our experiment. So we can preserve the coherence for a much longer time, which is actually limited by the theoretical limit, which is the natural lifetime of the Rydberg state. But the efficiency due to the higher diffraction order is quite low. So we actually developed later a better method to do that. So instead of performing a phase modulation, we actually are transferring the atoms to a different state, and at the same time kicking the atoms in the one particular direction. So at the end, we can make the phase of the spin wave like a constant. So this happens in a way that we just have a 2-photon transition between the 2 actually ground state using the one intermediate state. So the atoms are absorbing 1 photon and emitting a different photon. So we have a momentum transfer, and this momentum transfer is actually the same as the momentum transfer that was induced during the preparation process. So we are actually not exactly cancelling the motion induced by the first process, the excitation process, but we are kicking all of the atoms to follow the Rydberg atom. So we are spinning the atoms up, so the velocity difference between the Rydberg atom and all of the ground atoms is again 0 as it was at the beginning. Okay, so why we are doing all of that? Because we wanted to use our atom for microwave sensing again, and for this we need for this longer time that we have to interact with the microwave field, improves the sensitivity. So we developed this method to elongate the coherence time. So we have the so we can store we can preserve the Rydberg state in this collective excitation in our cloud for a longer time, and during the waiting time, the storage time, let's say, we can introduce a microwave radiation to the chamber. So we have again interaction between two Rydberg states induced by the microwave field, and for example we can observe those Rabi fringes. So we are performing so in this basic experiment we are introducing the microwave field for a given time. And after this time, we are performing the readout, which actually corresponds to measuring the population in the original Rydberg state. And for this, we can see those nice fringes. We can also plot this map, which is map of the microwave power and the tuning. And this is a computed map from the theory, and you can see that it nicely matches the experimental result. But strange thing happens when we increase the amount of the Rydberg atoms that we are preparing. So the previous slides were for a regime in which we have only small amount of Rydberg atoms, and we increase the probe laser and do the same experiment again, and also introduce some additional waiting time. We'll observe that instead of like a nice sine wave, we're getting these distorted fringes, which are very sharp around the maximal points. So we thought that this is really nice. Because it means that, so because it means that in those regions, the peaks are sharper, which means that we can have more information about the phase of the Rabi rotation that we induce in the experiment. So we started exploring this effect, and we actually saw that this effect is due to the interaction between two Rydberg states, which we can model using this simple scattering Hamiltonian. So we have so D and P are those spin waves in two different Rydberg states, and they are interacting with each other with a potential that is dipole potential. And due to the interaction, the phase of the spin waves is getting scrambled, so which means that we are generating a spin waves with different wave vectors, but only wave vectors which are satisfying the phase matching conditions are coupled to the light. So at the end, we see losses. And we can model that by taking all of the modes that are not k equals 0 modes, let's say, which is the k that is coupled to the light at the end, as environment, and only concentrating about the modes that we actually observe in the experiment. So we can have this jump operator that is actually scrambling the coherence between in the spin waves. And from this, we will have this, if we plug this jump operator into Lindblad equation, we end up with this evolution of the operators for the spin waves. So we have like a decay, which is controlled by the amount of the spin waves in the second mode, actually at the beginning. So this simple model actually nicely explains what we see in the experiment. So we can control the population in the two different Rydberg states using just the microwave pulses. So we can bring the atoms to the second Rydberg level using the microwave pulse. So doing just a rotation, and then introducing some interaction time, and during the readout we can observe this decay curves, which nicely correspond to this model. So we wanted to build a quantum metrology setup around this effect. So we end up with this setup, and so at the input we have coherent state. Then we have a beam splitter, in which we have the theta, which is the rotation angle of the Rabi oscillation, which controls the transmission into the two different modes. So those are corresponding to the two different Rydberg states. And then we have the interaction, which introduces losses of the state that we are observing in the experiment at the end. And at the end, we have our experimental losses that are always present in the experiment. So if we take this model, we can write down those operator transformations, and we can calculate actually by. So we are starting with a coherent state, and we are actually calculate the statistics of the photon statistics at the output, and so we can plot, for example, the mean and variance. So we indeed observe that the sharper peaks, which is nice, but we pay for that with increased variance. So can we gain something from that if we observe this increased variance? But this is for eta equal 1. So let's see what happens if we introduce some losses. So for losses, in our case, when the losses are happening at the end of the process, so after the interaction. So again, for eta equal 1, so no losses, we observe this increase of variance and also the sharper peaks. But if we introduce losses, the sharper peaks are preserved and the variance is dropping. And actually for smaller etas is approaching the variance equals mean, which means that we have a coherent state. And we can also calculate future information for this measurement scheme. So this is future information associated with measuring the angle of the rotation, so the theta. And although on those plots, the future information and mean are divided by the eta. So we are just normalizing it. And as you can see, for the losses at the end, we can have even that the variance is increasing, we can, because of the losses, the feature can be still high, which doesn't happen in the case so for the losses at the beginning, we have this normal situation. So actually, the gain comes from the fact that we have the losses and the normal. So here we are comparing two schemes. One is with the losses, and one is with the losses but without the interaction. And the question is if the interaction helps with determining the theta. And the answer is yes, because with the losses we have those sharper peaks, and the variance stays at the level of a coherent state because of the losses. And without the interaction, we'll have a normal sine function here. So we have a Fisher, so the quantum Fisher equal to 1. But if we renormalize the Fisher, so the quantum Fisher will be, normally will be multiplied by the efficiency, the eta. But if we, in those two cases, if we normalize the Fisher, we can observe that we can have again, in the losses scenario, we can have improvement over normal measurement without the additional losses. And in our case, the improvement can reach a factor of over a 2. Yeah. And with that, I would like to thank you for attention.
Thanks, Mateusz, for a nice overview of all the Rydberg sensing and experiment done in your lab. So let's take questions from the floor maybe first. I mean, students are strongly encouraged, as they always do, because they get extra points. Anything?
Maybe what is the efficiency of your setup, of this conversion?
Oh, the conversion.
Which part, the warm atoms or?
It depends how you define the efficiency.
Okay, so you can define power efficiency and...
Yeah, but the problem here is that the interaction medium is much smaller than the wavelength. So first of that, you have this coefficient that corresponds to the difference of the cross section of your absorber, and the smallest possible beam, microwave beam that you can have, which is like a factor of few orders of magnitude. But you can calculate actually you can neglect that effect and say that you can make your atomic medium very large. And if you calculate the efficiency that way, you will obtain like a few percent of efficiency.
But this is power efficiency, yes?
Yes.
So...
Yeah. So, yeah. No, sorry. It's a photon per photon efficiency. Yeah.
Okay, then I have a question, because you had this plot of statistics when you increased the, it was the first part that you were kind of approaching coherent light by increasing the strength of antenna.
Mm-hmm.
So this is a trivial question, because it's not that easy to do coherent light in reality, you need the laser. So with microwave photons, how you guys created coherent light?
So you just take
a cavity?
No, just generator phase log loop, which is essentially a laser.
Okay, so basically a normal antenna, if I plug it, it will create thermal microwave photons, but there's an easy way of creating coherent microwave.
I would say it's harder to create thermal microwave radiation than coherent, because all of the devices that are generating microwaves are actually coherent, because this is just a resonator, right?
Okay, so you are driving electrons up and down at a given frequency. I don't care what's called, but it's because it's an electronic circuit that generates.
Yeah. So we have like a
okay.
electronic resonator. Like
okay.
LCC circuit, so it's generating coherent.
Okay, and then my second question was returning to what Marcin asked. So so you have the warm atoms. Let's mind the efficiency.
Mm-hmm.
But now you go to cold atoms.
Mm-hmm.
So what's the improvement already in the efficiency? And then on top, you're starting playing with some, let's say you added this phase-preserving extra beams. So first of all, what's the point of going to cold atoms in terms of efficiency? And then you even start playing on top of it. So I couldn't get what are maybe some numbers, I don't know.
So in terms of efficiency, I don't know if there is a gain.
Or maybe sensitivity to what kind of microwaves you can measure.
Yeah. So we are still in the process of comparing those two two methods. As you saw, this is the last setup is that I think that we are currently working on. So our first, let's say, hand waving calculations show that we can mostly reach the same levels of sensitivity, but we can improve that by for example, the efficiency can be improved by coupling the atoms to the microwave cavity. So we have the microwave interacts many times with the same medium.
Because you argued first that by making them cold, you get rid of Doppler broadening, you get rid of...
Yeah, but the Doppler broadening actually helps sometimes because you can have like the bandwidth of your receiver can be larger because of that. You can
so
also...
So it's not clear whether cold are better than warm. This is
the cold are definitely better for a quantum stuff, right? So, for example, you can build
this qubit.
Yes, and there is actually one demonstration of a converter working on the based on cold atoms, which are coupled to the cavity, and the cavity is cooled, so you don't have this microwave thermal radiation, and then the efficiency can be very high, and you can actually observe some quantum effects on the microwave photons.
Any more questions? Anything from the floor?
Another advantage of the cold atoms is that you can, for example, as I showed you, you can design so sophisticated measurement schemes.
Yes, to do quantum, so it's really to engineer quantum states, no?
Yeah.
So this is your answer.
Yeah.
If you want to build a sensor, it just cares about intensity, use the electromagnetic induced transparency.
If you want to build a sensor to do something practical, take a glass cell.
If you want to create superposition of different Rydberg levels, you got to play with spin waves.
Yeah.
Okay, let's take it as a home message, unless someone has questions. No, then let's thank Mateusz once more. And we gather next week at the same time, hopefully without delay. Have a good week.